All right, it is 3 minutes past, and I want to welcome everybody to this second installment of a mini course by Amol, and please give your full and undivided attention to the screen and Amol's presentation.
Thanks, Andre. So let me just start by recapping what we talked about last time. So we started by stating this result for the large genus asymptotics of intersection numbers. What I owe you this time then is a proof of this result through the recursion or through the Virasoro constraints that define them. Then we proceeded to describe a series of applications for these large genus asymptotic results. The first were for the limiting statistics of random square-tiled surfaces. So the way in which this went was that we associated with each square-tiled surface a stable graph gamma, and all of the statistics, or all the relevant ones that I was describing in my previous talk, were determined by this graph gamma, and therefore the question of analyzing their statistics amounted to counting how many square-tiled surfaces existed that were associated with the given graph gamma. So we then stated, and what I owe you this time is maybe a proof of the expression for this count through the intersection numbers. Another application was to the volume of certain moduli spaces. So the way in which this went was that we could discretize this volume of the moduli space QGN. So QGN denotes the set of quadratic differentials of genus G with n simple poles. So you can discretize this moduli space through square-tiled surfaces. So by doing this discretization, this showed that you can write the volume of this moduli space as a sum over gamma of all square-tiled surfaces whose stable graph is given by gamma. So the previous point, the expression of this count through intersection numbers implies a formula for these volumes through intersection numbers. So, and I won't go into this volume statement anymore in this talk. The third application was to certain counting problems. So, which is known as the question of analyzing the Siegel-Veitch constant. So I remind you that the Siegel-Veitch constant, this area Siegel-Veitch constant, counts weighted by area the number of maximal cylinders on a surface. So I stated last time a formula for this Siegel-Veitch constant in terms of the volume. And so what I owe you this time is maybe an explanation of where this formula comes from. So an outline for this talk then is that I'll start by trying to outline a proof of the large genus asymptotics for these intersection numbers. And then after doing that, I'll proceed to describe how to obtain these expressions for these contributions of square-tiled surface counts through these intersection numbers. And then if I have time, I will just quickly give a sketch of maybe of where these formulas for these Siegel-Veitch constants come from in terms of the volume. So I'll try to do points 1 and 2 in fairly precise detail, but then maybe the third one I'll be much more sketchy on. Okay, so let's start with these intersection numbers. So remember that we had these psi classes, psi1, psi2, all the way up to psi n on this moduli space MGN. And we have this correlator or this intersection number defined by tau d1, tau d2, all the way to tau dn, which is the integral over the moduli space of the product of psi I to the di. And the theorem stated that if I fix any d corresponding to an intersection number of genus G with n marked points, then as G tends to infinity, this intersection number tau d1 all the way to tau dn, it converges to some explicitly factored product uniformly in D, as long as n is little o squared of G. So the main tool for proving this result will be based on the recursive formulas of the Virasoro constraints that describe these intersection numbers. So any recursion requires initial data, and the initial data is given by setting tau 0 cubed equal to 1 and tau 1 equal to 1 over 24. And now the Virasoro constraints are given by this recursion stated over here. So on the left side, we see an intersection number, tau k plus 1, then tau d1 all the way to tau dn. And on the right side, we see a family, like a sum of other intersection numbers. So the left side is the guy we're trying to compute. The right side is somehow of lower complexity. And the reason it's of lower complexity is that the dimension 3g plus n minus 3 of the moduli space on the left is bigger than that on the right. So in principle, if I keep on applying this recursion, I can reduce this dimension down to 0 or 1, and that will reduce me to the initial data. So using this recursion, you can show, although it's maybe not entirely obvious if you just stare at this immediately, is that the 1-point correlator is explicit, namely tau 3g minus 2 is equal to 1 over 24 to the g times g factorial. So it will be useful for me to describe a normalization of these correlators, which is the one that I'm admittedly more used to. So I'll simply divide out, so I'll define this normalization of the correlator bracket D by the intersection number tau d1 all the way to tau dn divided by the asymptotic value that I had stated in my previous theorem. So of course, under this new normalization, the theorem states that this bracket D tends to 1 as g tends to infinity uniformly in D as long as n is little o square root of g. And I'll translate a few of the results in the previous slide under this new normalization. So first is that we have this normalized initial data, which states that this, the 0, 0, 0 bracket is equal to 1, and that's also equal to bracket 1. And the second is that under this normalization, we have the 1-point function is also equal to 1, namely 3g minus 2, bracket of that is equal to 1. So these are both exact statements. So the theorem is exact in those two cases. I'll also state, because we'll need it later, as a 2-point limit. So if I take a 2-point correlator of the form d1, d2, corresponding to an intersection number of genus G with 2 marked points, this will behave like 1 plus order 1 over G. So the proof of this result was based on an exact formula for the 2-point correlator. You can prove this exact formula in various ways. One of them is directly with the Virasoro constraints. There are also other proofs based on generating series for these correlators. You can see, for example, the works of Faber, Pandler, and Zagia or Andre. So in any case, one has a limiting statement for the 2-point correlator. I should say that you also have exact formulas. I mean, for n-point correlators themselves, except they're vastly more complicated, and it's not clear to me. Well, I didn't try too hard one way or the other to see whether or not one could extract asymptotics from those formulas, but I'm a little bit more frightened, especially if n goes to infinity, because those formulas get exponentially more complicated in n. Anyway, so I will also state what happens to the Virasoro constraints under this normalization. I mean, it transforms. I mean, I've written down the expression.
No, that's not true. I mean, the formula we discussed last time is that the fact that these are like, this is what this expectation of like Laplace transform of the Airy point process.
Yeah.
Like the complexity of that formula, the length of that formula is linear in n. It requires like,
yeah. So I looked in. I'm still having trouble with sound. You're asking about the connection between the intersection numbers and the Laplace transform for the Airy kernel. Am I right, Andre?
Yeah, all I'm saying is that, it depends on how you write these formulas. They're certainly not, you can certainly write them in shape which are not exponentially complicated in n.
Yeah, that's right. So, I mean, one can do that. That's right. So one can write these intersection numbers, at least these generating series for the intersection numbers in terms of as a linear combination of Laplace transforms of the Airy kernel. When one does that, one actually finds something quite nice happen, which is that so I looked into, I quickly looked at it, which is that if the x's involved, I mean the x's, the variables in the generating series tend to infinity, these generating series are actually given by linear combinations of these Laplace transforms. And then as long as all the x's tend to infinity, what happens is that actually something nice happens, which is that the linear combination actually gets supported asymptotically on one term, which is the 1-point Airy, which is the 1-point the Laplace transform of just the Airy kernel itself. So like the 1-point Laplace transform. So that's quite nice, although it wasn't clear to me how to I wasn't directly seeing how to extract asymptotics for that, because, for example, well, okay, I can go into more detail about the difficulties later, but yeah, I mean, so I guess my point on that is that something very nice happens even in the asymptotic limit when one understands this interpretation through the Airy kernel. Although I still wasn't quite seeing how to prove this theorem from that. Yeah. Okay.
Sure. Thanks.
Yeah. Okay. So I'll describe another argument though, and that's with these Virasoro constraints. So as I mentioned, these Virasoro constraints, they transform under this change of variables. And the reason I'm writing this down so explicitly at the moment is that if I look at the sums of these coefficients, so for example, 2dj plus 1 over 6g plus 2n minus 3, if I look at the sum of those and the sum of this 12g over this quadratic, et cetera, if I analyze the sum of those and just perform basic arithmetic, what I'll see is that this coefficient sum behaves like 1 plus order n over g as g tends to infinity. So g is much larger than n. So this is at least consistent with the claim that this intersection number behaves like 1, because if I plug 1 in on all the right sides here, the claim is that I'll get 1 on the 1 plus maybe a little bit of error on the left side. So in principle, one could just imagine using this to prove the theorem. But the problem is that, I mean, again, since the initial data is just given by 1, but the problem is that the recursion has to be applied many times in order to reduce to the initial data. In particular, you require order G applications of this recursion, since each application reduces the dimension, this dimension 3g plus n minus 3 by about 1. I mean, some might reduce it by 1 or 2, but I mean, order 1 basically. So each step then induces a multiplicative error of 1 plus order n over g. And therefore, if I raise this thing to the g, that sort of suggests that you can prove a bound of this normalized correlator d bracket by order e to the exponential order n. So that can be shown directly through the recursion. And so I'll just state a proposition that to such an effect, this proposition will actually be later, will be useful as sort of an a priori bound later on. So the statement is that for any g and n, such that without any restrictions on n and g, so I no longer impose that n is given by little o of the square root of g, then this normalized correlator d bracket, it's bounded by 3/2 to the n minus 1. Okay, so again, this is sort of just by direct insertion into the Virasoro constraints. I put in that bound on the right side, and then I get it back on the left side by sort of a painful arithmetic. I don't think it's very enlightening for me to go through that, but sort of this is just proven by direct induction. So I should just mention as maybe an aside curiosity is that this exponent 3/2 is optimal, since this correlator, if I set the genus to be 0, and I have n minus 3 ones followed by 3 zeros, this correlator behaves like a polynomial in n times 3/2 to the n minus 1. So, so yeah, this 3/2 can't be reduced by anything. And this condition n is equal to what this sort of suggests or implies directly is that you need some sort of condition on n to get the asymptotic I stated before, which is you need n to be little of square root of g in order to get that asymptotic that this bracket d tends to 1. So now let me try to explain how to use these Virasoro constraints to prove such an asymptotic result. So I've just restated the recursion over here, but I've colored various terms. So let me just go into detail into what each term does. So I have this blue term here, which takes this k plus 1 and finds some place to insert it in D. So I take some coordinate dj, I add k to it, I leave all the others the same, and then I multiply it by some coefficient, which is 2dj plus 1 over 6g plus 2n minus 3. So this blue term decreases the value of n because it's sort of absorbing the k plus 1 into the d. The second term, which is the red term, it splits up k minus 1 into an r and an s, and then it replaces k plus 1 with an r and an s. So what this is doing then is it's increasing the value of n here. And then we have the final term, which is this green term here, which typically decreases n, and now it's quadratic in the correlator. So what it's doing is that it's both splitting k minus 1 into an r and s, and then it's also splitting the coordinates of d into two sets I and j, into two disjoint sets I and j. And then I have this coefficient here multiplied by this product of correlators with r and then d restricted to the subset I, and then s with d restricted to the subset j. So this green term will be asymptotically negligible in the sense that these coefficients here, the sum of all of them, it behaves like O of n over g squared. So I will not really consider it in what follows.
I had a question about the previous transparency.
Yeah.
Yeah. So if we go, can we go up to the previous slide?
Yeah, previous slide.
Yeah. So this is so if I look at these insertions, of course, tau 0 can be removed by the string equation, and tau 1 can be removed by the dilaton equation. and all the other ones, they kind of really eat up the dimension, right? So if I add a marked point, then if I don't put anything, I increase the dimension. If I put tau1, that's exactly the same dimension, and all the rest I lose the dimension, right?
That's right.
And so people have, especially I think Giventhal is very, is a big kind of proponent of that, make this kind of dilaton shift to remove that tau1 altogether. Just from your generating series, you just remove tau1.
Yeah.
Is that does that gets any easier, since you seem to be saying that this kind of the number of ones is the actual kind of, it's like the first pole in this generating series comes from the ones.
So you're exactly right, Andre. So this is actually in relation to something that Noah was asking last time, which was this condition of n is little of square root of g. So I think that if this d doesn't have any ones in it, then this asymptotic becomes exact for n is equal to little of g. So in that sense, if you sort of remove all the ones, and moreover, you can sort of, as you mentioned, by the simplest forms of the Virasoro constraints, one can remove the ones directly, and you can explicitly understand the contribution of these few ones to the intersection number. So in that sense, I mean, sort of by removing the ones, you can at least extend the range of these results. But beyond that, it's more than the ones that form a problem. If n contributes to the dimension of the moduli space, the twos and the threes will also cause problems. I'm not sure if I've...
Yeah. Oh yeah, sure, thanks. But is it, yeah.
Sorry, but is it what?
No, that's all. Thanks.
Okay. Okay. Yeah.
I guess what I was trying to say is that if you can, maybe you can just do the dilaton shift systematically, and there's like good algebra to do it, and just work with that reduced kind of invariance.
You're saying that I can do the shifts automatically? Wait, sorry?
Yeah, there's this. I mean, it's not very complicated, but there is a simple algebra of how to remove all the ones. It's whatever.
Yeah. I'm saying you can do that.
Yeah.
Yeah, I agree that you can do that. And I'm saying it does. You can learn something from doing that. Although, yeah, I mean, yeah, I guess what I'm saying is that I agree that something like this is possible, and you could sort of extend the range of this theorem if you do something like that. Although, after you do that, I mean, it still requires work to show something like this. The ones are sort of not the only problem in proving this theorem. Yeah. Okay. Anyway, yeah. So as I said, this blue term, it decreases the value of n. This red term, it increases the value of n, and this green term is more or less asymptotically negligible. So I mean, the point is that we understand this correlator for small values of n. For small values of n, in particular, the 1-point correlator is just exactly given by 1, as I mentioned before, and the 2-point correlator is given by 1 plus order 1 over g. So one would in principle like to use these Virasoro constraints to reduce the value of n. In particular, if I were able to do this, then I would only require order n applications of this recursion. But of course, the issue is coming in this red term. It increases n. So if I repeatedly apply this recursion, then I get a larger value of n. And this red term is not asymptotically negligible unlike the green term, so I can't just drop it. So the effect of this red term is partially counteracted by the effect of this blue term, which decreases n. So what we'll show is that the effect of the blue term basically dominates that of the red term through a comparison to a random walk. So the spatial variable of the random walk will be n, and the time variable will more or less be the number of applications of the recursion. So I'll quickly describe a heuristic for how this goes, and then I will spend a few slides describing this heuristic. So we wish to, let's say we want to evaluate some bracket D, where D is some n plus 1 tuple of numbers d1 all the way up to dn plus 1. We'll let k plus 1 denote the smallest di, and then we'll let little d denote capital D with I mean, basically, I just drop off this minimal value from capital D. So now little d is an n plus 1 tuple. So then by definition, this bracket D is equal to bracket of k plus 1 of little d. And then the Virasoro constraints tell me that this is going to be given by a sum of a red term plus a blue term plus a small term. So I'll let A denote the sum of the coefficients of the blue, and I'll let B denote the sum of the coefficients of the red. And as I mentioned before, you can quickly show that the sum of the A plus B is of order 1 plus some little error, or n over g. Yeah, and maybe more precisely, what we can say is that A plus B is between 1 minus 1 over g and 1 plus n over g. So let me pretend, just for the sake of explaining how this random walk works, that A plus B is exactly equal to 1, in which case you can view this recursion as, and let's say we also drop off the small term, you can view this recursion as sort of a Markov process, in the sense that you sort of jump from capital D to a D prime with certain probabilities. So more specifically, we can say flip a coin, and this coin will tell me whether or not I go red or blue. With probability A over A plus B, I hit heads, which is going to be blue, and with probability B over A plus B, I hit tails, which will be red. So then if I hit tails, then I select some D prime, some blue D prime with probability A D prime over A. If I hit tails, then I select D prime with some probability B D prime over B. So then I swap out D with D prime, and I also swap out Gn plus 1 with G prime n prime plus 1, where G prime n prime plus 1 are the corresponding pair for D prime. So in particular, if I hit heads, then n prime is n minus 1, and if I hit tails, then n prime is n plus 1. So this decreases n with probability A, and it increases n with probability B, more or less. And then I repeat this many times, and then the output is that I would say that the expectation of this normalized correlator of D prime is serving as an approximation for the original correlator I was trying to compute. So if there was no small term, and if A plus B was exactly equal to 1, this would no longer be an approximation, it would actually be precise, which is, I guess, an approximation. Anyway, yeah. So, okay, so to reiterate, I have this sort of random walk, and with probability, this n, it decreases with probability A, and it increases with probability B. And I have this asymptotic result for this bracket D that holds for n in 0 and 1. So if I assume that n is at least 2, then after many repetitions of this after I iterate this jump process many times, I eventually want n to decrease to 1. So what that means is that I want this random walk to have negative drift, so I want for B to be less than A. So now I'll have to compute. So I have that B. So if I remember the Virasoro constraints, they look like this. So now I've written down the coefficients for B. They're all the same. This 12g over this quadratic term. So in particular, I have k summand. So this B is equal to 12gk over 6g plus 2n minus 3 times 6g plus 2n minus 5. Let me now compute k. I mean, this is one of the few calculations I'll do in this slide. So k is the smallest of the di. So in particular, k plus 1 times n plus 1, which is the number of terms, is at most equal to the size of d. And I remind you that the size of d is equal to 3g plus n plus 1 minus 3. Again, I'm using the fact that k is smallest here. So if I shuffle this around, what you'll get is that k is at most 3g minus 3 over n plus 1. Okay. So now if I plug this in here, what you get is that b is at most 1 over n plus 1. This 1 over n plus 1 times 12g times 3g minus 3 over this guy here, 6g plus 2n minus 3 times 6g plus 2n minus 5. The top here is less than 36g squared. The bottom here is about 36g squared. So this is at most 1 over n plus 1, which is at most a third if n is at least 2. So what this is indicating is that since a plus b is at least 1, thus b is at most a third. That means that a is at least 2/3. So the random walk has drift about minus a third. So after like 3 n steps, you expect n to decrease down to 2. So what this is suggesting is that, see, if I apply the Virasoro constraints 4 n times, then this n prime is dropping down to 2. So what this is suggesting is that the expectation of this, this d prime is about d prime at some g prime n prime is most likely 2. So this is probably going to behave something like some normalized correlator of g prime with just 2 parts, and as I mentioned before, that's behaving like 1. So this is all heuristic. Any questions about the heuristic?
Yeah, sorry. Yeah, I have a question. So this is Virasoro constraints are about some linear operator, right? And
yeah,
I mean, and your Markov process is another linear operator.
yeah.
And is that, can you phrase this heuristic as just, just some kind of, conjugate going to a slightly different basis and applying your the procedure to just slightly changing the basis of function, slightly conjugating your operator? Can you phrase that? But what's happening in this transparency in this way?
I'm guessing that you can. Well, wait, hang on. But the Virasoro constraint is not linear, right? I mean, it has the quadratic term. But you're saying.
Well, I mean, you apply a linear operator to an exponential function, right? That's
yeah,
what Virasoro
right.
constraint looks like.
Yeah.
And so, is there some? Well,
I know. Okay, I see what you mean. I see what you mean. Yeah.
I'm trying to ask whether this is what is this heuristic can be. Well, I don't know. Maybe you're going to make this heuristic tight as it stands, but I was going to suggest that maybe this can be made a little tighter if you can say, well, we can rewrite the equation so that we see more clearly what's happening.
Yeah, that might be possible. I haven't tried it, but I would imagine that something like that should be doable. Yeah, although I don't have an answer for you immediately.
Okay.
Anyway, okay, I'll make this precise again through the sort of random walk interpretation. Okay, so for any, the proof consists of an upper bound.
Sorry, Amol, can I ask a question about the previous slide?
Yeah.
Maybe I'm missing something obvious. So in the second to last line, there's a 3n, and the last line there's a 4n.
Well, yeah, I mean, it's true for both. So I mean,
okay.
The random walk should maybe I need to go a little bit bigger than the random walk decreases by 1/3 per step. So after maybe anything larger than 3 steps, it decreases down to 2.
Okay.
Yeah.
Thanks.
Yeah.
Can we relate the 2/3 coming for A here to the bound we had in terms of 3/2 earlier?
Those are different. Those are different inversions of those seem to be different inversions of 3/2.
Okay.
Yeah. Yeah, I mean, like maybe quickly you can see. I mean, this is really not 3/2. This is 1 over n plus 1, is what you should really be thinking of this as. But that 3/2 before came from, making n very large.
Okay.
Yeah.
Thanks.
Okay. Yeah. Okay. So let me now proceed to make this a little bit more precise. So we can define theta of Gn to be, okay. So I'll take the infimum over all. So again, as I mentioned before, the proof will proceed through an upper bound and a lower bound. For the lower bound, we take the infimum over all G's, big G's bigger than little g, and the minimum. So I basically make G as large as I can, as large as I want, and I let n be as small as I want below this n, and then I let theta G of n denote the minimum of all such correlators under those constraints, and then I'll define this random walk Wn of t with the initial data W of n of 0 is equal to n. So the first thing it will do is it will absorb at n equals 2. What that means is that if W n of t minus 1 is equal to 2, then I set it equal to 2 for all subsequent times. And the second is jumps. So I set Wn of t to be Wn of t minus 1 with probability 2/3 and equal to Wn of t plus 1 with probability 1/3. So the proposition is that for any n, at least 2, and any, say, G that's at least t plus n, then this theta of G of n, this bound here, is at least going to be some factor times the expectation of theta of G minus t. And then the important point now is that this n is evolving according to this random walk W. So it's theta of G minus t, Wn of t times some prefactor here. So in particular, this will imply, if you have a proposition like this implies the lower bound, because n is little o of g. In fact, it's little o of square root of g. So by setting t is equal to 10n plus maybe a little bit, I will get that this prefactor here is 1 plus little o of 1. And then this expectation, it's also bounded below by 1 plus little o of 1. This should be bounded below by that. And the reason is that by the law of large numbers, I know that I have Wn of t is equal to 2 with probability 1 minus little o of 1. And then the exact or asymptotic result will tell me that this theta of g of 2 is equal to 1 minus little o of 1 with for n, for n between 1 and 2. So this guy here is going to be 1 with probability 1 minus little o of 1. And that gives me that this is lower bounded by 1. And likewise, this prefactor is also about 1. So I immediately get this lower bound of theta of g of n being about 1, bounded below. So to prove this result, I mean, once one writes it down, once one writes it down, it's like a fairly quick induction. I mean, so it's true if t equals 0. I mean, because Wn of 0 is equal to n. So if one wants to prove it for larger values of t, you fix some g and fix some n. So I can find some big G and some m such that theta g n plus 1 is equal to a correlator with these appropriate parameters. And then I apply the Virasoro constraints to it. I get a blue term, a red term, and a positive term. The positive term is positive, so it drops out. Then I have a blue term and a red term. I bound the blue terms above by below by theta of g of n now, not n plus 1, because the blue term, I remind you, decreased the value of n. The red term is bounded by capital B of theta of g minus 1. Now I have to increase the value of n to n plus 2. And then one can see that this is bounded below by a plus b times 2/3 times. You can basically pretend that a is 2/3 and b is 1/3. And here I'm not using anything too deep. I'm just using the fact that a is at least 2/3 and b is at least 1/3. B is at most 1/3, and an inequality between the thetas. I mean, okay, I mentioned in detail over here. You can basically prove this last inequality by an expansion, but importantly, one is using the fact that b is at most 1/3 and a is at least 2/3. So then one just repeatedly applies this bound. So theta of g plus n is at most this guy. But I remind you, but first we have that a plus b is at least 1 minus 1 over g. So I get this 1 minus 1 over g appearing here. And then second, I can interpret this linear combination here as an expectation value, in particular, this bullet point here, like 2/3 of theta of g minus 1, n plus 1/3 times theta of g minus 1 n plus 2 is equal to the expectation of theta of g minus 1 Wn of t. So I mean, this is just more or less the definition of expectation under this random walk. So one step of this application will tell me that theta g of n plus 1 is at least 1 minus 1 over g times the expectation of theta of g minus 1 times Wn of 1. But then I can iterate. I can keep applying it, and I will eventually reduce down to the to this sort of bound here. Okay, so that's the lower bound. Are there any questions about that? No. Okay, so I can then talk about the upper bound, which is similar. So I define this capital theta in a rather similar way. I replace all mins and imps with maxes and sups. And now the statement is that I can bound this theta of g of n by some prefactor times the expectation of theta. Okay, I reduced g by a little bit, but then again, the point is that we're replacing this n with this Wn of t. So okay, so now by setting t is equal to some big constant times n plus log of g or something like that, the prefactor is again 1 plus little o of 1. And here again, one should sort of imagine that you're for simplicity that just ignore the a lot of the bulk here. I mean, just imagine this is 1 plus n over g. So if you're taking t to be something like n, 100 times n, then this is going to look like 1 plus n squared over g. So this is where the condition that n is little o squared of g comes from. The prefactor is going to be 1 plus little o of 1 under the constraints that t and n are little o squared of g. And with high probability, we have that this w n of t is equal to 2. So what that means is that with high probability, this thing in the expectation, or this capital theta, is about equal to 1 plus little o of 1. So, I mean, this is looking good. You have the prefactor here, which is about equal to 1. I have with high probability, the thing inside the expectation is about equal to 1. But the problem is that this unlikely event, you have some chance that this Wn of t is going to be at least 2. So, I mean, the chances of that happening is rather low. But on that event, if this theta is just massive on that event, I'm going to run into serious problems. That could non-trivially contribute to the expectation in that scenario. So you require this sort of a weak upper bound, or what we call a tail estimate, on this theta g of n that will apply on the event that this Wn of t is rather large. And that's where that sort of a priori estimate came from. The bound, the 3 halves to the n minus 1 bound came from. So with that, one could say that this theta g of n is bounded above by, so this should say expectation of theta g of n is bounded above by, first I can restrict to the event that Wn of t is equal to 2, and then I can sort of sum over all possible values of Wn of t that are bigger than 2. So I sum from k equals 3 to infinity that Wn of t is equal to k. So I have the sum over here. The first thing is going to give me, I mean, just by the fact that I know the asymptotics when n is equal to 2 is going to give me 1 plus little of 1. The second, I know I use this proposition here to bound the theta by 3 halves to the k. And then I have the probability, after I pull out the theta, I have the probability that Wn of t is equal to k. Okay, but then I can just use sort of standard estimates on the large deviations for this random walk. I can compute the probability. This is like the simplest thing on probability. You can just compute the chance that this random walk is equal to k, and that will swamp out this term here. That will kill. I mean, it's going to scale like 1 over 2 to the k kind of times some. So I wrote it down here in particular. It's going to, for a large value of k, the probability that this Wn of t of k is equal to k is going to scale like 2 to the n minus k for k large, and it's going to scale like 1 over, much less than 1 over g for k small. And by putting those together in here, you'll get the required upper bound of 1 plus little of 1. Okay, so that was. So are there any questions? So that's all I'll say about the these asymptotics for the intersection numbers. So are there any questions about that?
I have a slightly random question.
Yeah.
And so these are not Virasoro constraints. It's only roughly 1/2 of the Virasoro algebra is acting. So only the like differential operator on the line, something like that, like right. So this is, you start with L0, L1, and so forth.
Yeah.
And so I don't know, I never thought about this, but I imagine something like this is probably not rigid. So there may be other ways for Virasoro to act.
Okay.
But I mean, they maybe, of course, if it differs by conjugation, that's not so interesting. But let's suppose you have some kind of, suppose there exists a nearby Virasoro action. Is that that would, your argument would then, seems to me, would just go through unchanged, right? Is that? Or...
Yeah. That's right. I mean, yeah, I think I agree with what you say.
Okay. Yeah, I like I said, I have no idea whether these actions are rigid or not. But if they aren't, then the asymptotics is independent of what the details of the
that's right. I also have not looked into what other action. I mean, what other sort of action the Virasoro could have in this generating series. But yeah, I think that the sort of asymptotic framework is rather robust in the sense that it shouldn't care too much about it.
Okay. And it's and if I give you, like say, L0 and L2 generate this positive half of the Virasoro. If I give you these two operators, what do you think determines the asymptotics? Is that or is that some?
Just L0 and L2?
Yeah, well, they do this to generate, right?
Yeah, yeah. You mean to say, like, do I have a what would this result here would look like?
Yeah, exactly. Yeah.
I mean, okay, I wouldn't be able to say offhand. I would imagine it might have might have a somewhat similar form. Maybe some simple dependence on the DIs, and then just dependent on G after that. Although, yeah, okay, I can't say offhand.
Okay.
I might be wrong.
Okay. 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 Fair enough. Thanks.
Yeah. Okay. Any other questions? Okay. Okay. So then the next part we'll go into talking about how to count these square tiled surfaces. So I'll just start with a little bit of review on that point. So I remind you that a quadratic differential is a pair XQ, where X is a Riemann surface and Q has a quadratic differential on it. So locally Q is of the form f of z dz tensor dz, where f is a meromorphic function with all poles simple, and it acts rather easily. And I mean, one can easily understand it's how it changes variables. In particular, if I rewrite Q in the form of GW is equal to Q is equal to G of W dW tensor dW for some other local coordinate W, then f of z is equal to G of W times dW over dz squared. So these quadratic differentials, they define horizontal and vertical trajectories. So if I have some trajectory gamma from 0, 1 to x, which is a path on x, then I call this trajectory horizontal if f of gamma of t times gamma prime of t squared is a positive real number, and vertical if it's negative. So in particular, this whether or not it's horizontal or vertical prescribes whether or not this period, I mean this integral here, I mean this square root of f of z dz is real or imaginary. So if I sort of transform into this more natural coordinate for this quadratic differential given by the integral of the square root of f, it's telling me whether or not along this trajectory I'm real or I'm imaginary. So these trajectories give rise to horizontal or vertical foliations of x associated with q. I've drawn some pictures of how they look here. So the important point about these pictures is that if I have a zero of order k, and k can be -1 if you want as well, then there are k plus 2 horizontal or k plus 2 vertical trajectories emanating from such a zero. So maybe the most important example for what we'll talk about is here, z dz squared. So here you see this is 0 or 1, and I have three trajectories emanating from it. Okay, so a Jenkins-Strebel differential is a quadratic differential all of whose leaves under the horizontal foliation are closed. So in particular, this horizontal foliation will decompose the surface into a union of maximal cylinders. So I've drawn one over here where you have, this horizontal foliation is drawn here, and it's decomposing the surface into 6 cylinders, which are all colored in different colors. The singular layers are by definition the boundaries of these maximal cylinders, and they'll contain the zeros of the poles of the quadratic differential. So here, this is the surface of genus 3. It has no poles, so it has 4g minus 4, which is 8 zeros. You can see 4 of them over here. The other 4 will be on the opposite side, which if I flip over the surface, there will be 4 more there. So, and the singular layers are sort of determined by these black curves here. I mean, they'll connect 2 pairs of these conical singularities. So one on either, like this one and the one behind it. Okay, so each singular layer now will determine a metric ribbon graph. So the vertices of this graph are given by the singularities of the differential, the zeros of the poles of this, and the edges are given by the horizontal trajectories through the singularities. So in particular, for example, I have a singular layer corresponding to this vertex here. If I follow the horizontal trajectories through it, there will be 3 of them, and they'll connect to the zero on the other side, basically. And I'll have 4 such singular layers that correspond to 4 ribbon graphs, each with 2 vertices and three edges. So So we have vertices and edges. To define a metric ribbon graph, you also need the cyclic ordering and the lengths. Both of those are just given directly from the quadratic differential as well. So you get, in that way, you get a metric ribbon graph. So this gives you so the metric ribbon graph gives you a surface with boundary, and the number of boundary components in this metric ribbon graph is then given by the number of cylinders incident to the singular layer. So in particular here, I'll have 3 boundary components, and you'll have 3 cylinders attached to it. Okay, so now we're to recall a square-tiled surface. It's a quadratic differential whose periods are all in Zi. So so it's obtained by gluing a family of 1x1 squares, and these are special cases of quadratic of these Jenkins-Strebel differentials. As we discussed last time, we can create a stable graph from such a square-tiled surface X. So the vertices of this graph are given by the singular layers of X. The edges are given by the maximal cylinders in the decomposition coming from this horizontal foliation. And the genus of a vertex is given by the genus of the ribbon surface associated with the singular layer. So again, I had this picture last time as well. I have this quadratic differential, which is a square-tiled surface. I have 5 singular layers. One is this, 2, 3, 4, and 5. So those are the vertices of the graph. The edges are the horizontal or the cylinders, and these cylinders connect vertices because each cylinder is involved with 2 singular layers. And then the genus of the vertex will be, the genus of these vertices is going to be the genus of as I mentioned, just the genus of the ribbon graph you'll get coming from this singular layer. So now associated with each edge gamma, which each edge of E of gamma or each cylinder of X, we can associate a waist curve, gamma E, and then we can associate 2 parameters, which basically determine gamma from there. One is the length, WE, which is the length of the circumference of gamma E, and the second is this H of E, which is the height of the associated cylinders. So together, those just determine the cylinder. Okay, so what data do we need to recover the square-tiled surface? So if I fix some stable graph gamma, which has some vertex set V, some edge set E, and some genus decoration GV, and I let X denote some square-tiled surface associated with gamma, and I'll assume that X has all 0 simple and no poles. So what that means is that the associated quadratic differential is in the principal stratum Q of 4G minus 4 and then minus 1 to the 0. So no poles and all 0 simple. So to recover the square-tiled surface X, we'll need the following data. So the first is that for each edge of E of gamma, which I remind you is a cylinder of X, we require its length and its height. So the length is WE and its height is H of E. So next, we'll need a ribbon graph, so an integral metric trivalent ribbon graph, R of V associated with each vertex of V. So this ribbon graph R of V will satisfy certain conditions. The first, as I mentioned before, is that its genus has to match the genus under this decoration. So the genus of GV under the stable graph gamma. The second is that the cylinders attach to the boundary components of RV. So as I mentioned before, the cylinders will attach to the boundary components of RV. And what that means, that has 2 direct consequences. The first is that at any such ribbon graph RV, I have an equal number of boundary components. So the number of boundary components of RV is equal to the number of edges incident to V in gamma. The reason is that the number of edges incident to V in gamma is equal to the number of cylinders that are connected to the singular layer, and the number of boundary components in RV is equal to the number of each boundary component gives you a cylinder that's connected to that singular layer as well. So the numbers of those should be the same. The second is that the lengths of the boundary components of RV should be equal to these, should be given by the sets of cylinder circumferences, these WEs. So these WEs had better index the lengths of these boundary components RV. Okay, And the third restriction is that each vertex in RB has to correspond to a 0 of x, as I mentioned before. So since each 0 of x is of order 1, it's simple. This gives you the trivalence property. Remember that if you have a like a Jenkins-Strebel differential, and you have a 0 of order m, then the number of horizontal trajectories emanating from that 0 is m plus 2. M here is 1 everywhere, and therefore we have 3 horizontal trajectories emanating from each 0. This gives you this tells you that in each ribbon graph, since the edges of the ribbon graph are exactly given by the horizontal trajectories emanating from the vertices of the zeros, we see that each vertex in the ribbon graph is of degree 3. Okay, so this is giving you then an integral metric ribbon graph, trivalent ribbon graph with these properties. And hopefully this point here should give you some sort of reminder to the intersection number. I mean, as due to the theorem of Kontsevich, I mean, the intersection number sort of enumerates such ribbon graphs. Okay, and the third thing we need is a twist parameter. So I have these ribbon graphs at each vertex of the stable graph. I have the lengths and the heights of each cylinder, but then I need to know how to twist them in order to connect them along the boundaries. So for each boundary component of any RV, I need a twist parameter, which is some beta of beta, where beta is indexing the boundary component, which is going to be some integer between 0 and LB minus 1, and that's going to indicate the Dane twist for how I attach 2 cylinders along the boundary component. So here I've just drawn a quick example here. You have this genus 3 surface from before. It has 8 zeros, 4 of which are shown here and 4 of which are shown on the other side. These pairs of zeros will form singular layers under the horizontal foliation, and this gives rise to the stable graph gamma, which looks like this, which is shown here. The number of the edges of the stable graph correspond to the cylinders. So for example, emanating from this bottom left vertex, I have 3 edges. That's corresponding to the sort of yellow, green, and beige cylinder emanating from this 0 here. Then on each vertex of the stable graph, I'm going to have a ribbon graph, and that ribbon graph is always going to look like this ribbon graph over here, in the case of this vertex. So yeah, that's how you can recover the square tiled surface from the set of data. Okay, so I have a square tiled surface X, and I have some stable graph gamma associated with it. As I mentioned before, I have these 3 bullet points correspond to the data that I was describing before, that one needs to reconstruct X from it. So now let's turn to the question of enumerating square tiled surfaces. So let Sn of upper gamma denote the set of all genus G square tiled surfaces whose stable graph is gamma and has area at most n. I further let Rg of n denote the set of trivalent ribbon graphs with genus G and n boundary components, and we'll let nr of b1, b2, all the way to bn to denote the number of integral metric ribbon graphs whose underlying ribbon graph is some r and who has n boundary components of these lengths b1, b2, all the way to bn. So this is just notation. I think I had it in the previous talk too, but yeah, I recall that right over here. Okay, so now the claim is that the number of square tiled surfaces with area n and stable graph gamma is given by this sum over here. Right, so we have, I have various terms in the sum. Various entries in the sum. So let me just try to explain what they're doing. So first I have the sum over all vectors W and H. So W and H are indexed by the vertices of gamma. So this condition that W dot H is at most n. Remember the W's are telling you the widths of the cylinders, and H is telling you the heights of the cylinders. W dot H is therefore telling you the sum of the areas of all cylinders. Sorry, these are indexed by edges, not vertices. So these are WEs, not WVs. Yeah, so these are associated with the cylinders, and the statement that W.H is at most n is the statement that the sum of the areas of all cylinders is at most n. These WEs are, so that is explaining the sum here. I have to sum over all widths and heights. This product of WEs is now taking the product over all ways I can twist. So at each, along each, yeah, so I can, at each cylinder, I have WE possible ways of twisting it to connect it to another one. And now this sum over ribbon graphs here is telling me how I can sum over all possible ways of associating this ribbon graph at each vertex. So the second bullet point here, or maybe the second bullet point here, the number of ways I can associate a ribbon graph at each vertex of some genus GV with NV boundary components. And NV, I remind you that as I mentioned before, NV, the number of boundary components has to be equal to the number of edges incident to V in the original stable graph gamma. So now this orange term is NR of WE. This is telling you the number, this is enumerating now the number of such ribbon graphs with a whose boundary lengths are determined by this W. Remember, the boundary lengths of this ribbon graph have to be determined by the circumferences of these cylinders, because the cylinders are exactly attaching, are being attached to this ribbon graph. And these sort of violet terms are just symmetries, these automorphism counts that take all symmetries into account. So this is sort of an explicit formula for how many square tile surfaces there are with a given structure. Okay, so I've sort of recalled it here. And how does one eventually? Okay, so I mean, so basically, you to compute the number of ribbon graphs, you sum basically. So I've written down this exact formula here. I've had from the previous talk, I had described this linear functional Z on the set of monomials, which is defined by setting Z of this product x1 all the way to x1 to the m1, x2 to the m2 all the way to xn to the mn, given by this product of zeta functions and these factorials. And then I recall that the sum of the sum of these NRs weighted by automorphisms is going to be a polynomial in the variables. So in particular, that allows me to view this sum here as a polynomial. And so in particular, to compute this big sum here, I can just look at it monomial by monomial, and I've given a okay, I've computed it here. I mean, so I've taken just one monomial in this big polynomial here, and I've computed it under this sort of restriction here. So if I have some very large integer t, then the sum of all over all a and b, all vectors a and b, so that a dot b is at least t, you can compute it. The sum is going to be approximated by some integral. You know, I fix I mean, yeah, so instead of looking at a dot b, I can instead look at, you know, I can set ai bi equal to xi t. The restriction then is that the sum of the xi's is at most 1. And then you get some, by approximating this by an integral, you get something that looks like this. By collecting powers of t and powers of a, you see that the sum decouples from the product. So I get some global power of t here, and then I get some sum of inverted monomials, and then some integral, some beta type, some integral over the simplex, where the sums of the x's is at most 1. The sum here is exactly going to give you the product of zeta functions, and this integral over the simplex is going to give you a quotient of factorials here. So what you can quickly see is that this is equal to this prefactor of t to some power times exactly this z of this monomial. Okay, then I forgot to include this overall. I mean, this 1 over the sum of the ei factorial plus n factorial. The sum of this denominator here, that should also be included in the last line. So I mean, so that should indicate a few things. The first is that if t is very large, then the dominant term is therefore going to come when the sum of the e's is maximal. So therefore, the contribution to this big sum here is going to come when I only restrict to the top degree term of this polynomial here. Okay, and recall that this is given by this generating series for this intersection numbers. This top degree term k, which I denoted by k g of n, W1 all the way to Wn is going to be the leading contribution in N to this count over here. So I can replace this sum over ribbon graphs, this sort of weighted sum over here with these Ks, and what I will get is a formula that looks like this. This first bullet point here. As I mentioned before, if I perform the sum over on a fixed monomial, I will get some up to some constant. I will get some power of t multiplied by the z, and therefore, and the third point is that this k is given, as I mentioned before, by a generating series for intersection numbers. So that's this third bullet point here. So if I plug all these in together, what I will get is something that looks like some constant times some power of n times some z times the z evaluated at this big polynomial now. Okay, so one can sort of pull out all the n's, and we'll eventually get an expression that looks like some constant times some power of n times the z applied to a product of these k polynomials. And this is exactly what I had before. This is exactly the type of formula that I had mentioned in the previous talk. The number of square tile surfaces is given by this quantity, and if I want to compute the volume, then I have to divide out by n to the 6g minus 6. So this is sort of recovering this theorem that I had mentioned from the previous slide. The contribution to the volume coming from this stable graph gamma is going to be given by the z applied to this product of these k's, and maybe with some other w's, another monomial involved. So are there any questions about that?
So could you go one slide back for a moment?
Yeah. Yeah.
What was this n sub r? Big N sub r?
And sorry?
This big N sub r.
These ones? Wait.
For example, to the top.
Oh, this one.
Yeah.
This is okay, it's a lot of notation, I guess. This is okay, yeah, this was what? Oh yeah, okay, it's here.
Okay.
It's counting the number of trivalent metric ribbon graphs with certain boundary lengths. So these B's tell you the boundary lengths of the metric ribbon graph, and the R tells you sort of the base ribbon graph. And then you're asking, how many ways are there to assign lengths to the edges of the ribbon graphs in order to get these as boundary lengths?
Mm-hmm. Yeah, thank you.
Are there any other questions? Okay. Okay, yeah. So this is all I will have to say about these volumes of the correlators. One thing I want to mention though is that maybe so this doesn't use the geometric interpretations of these intersection numbers, right? I mean, it gives you it's using the fact that these intersection numbers are related to trivalent to counts of trivalent ribbon graphs. So I should say that there is sort of an alternative way of getting to a formula that looks like this, that might be viewed as more geometric, although I won't go into it. I'll just say in words what's involved in such an argument. So the argument, I mean, I guess it proceeds through hyperbolic geometry. So one can look at the way Peterson volume on the moduli space of hyperbolic surfaces, and it's a theorem of Mirzakhani that those can be the volumes of those moduli spaces can be expressed in terms of intersection numbers, and the proof of that is at least more geometric than more algebra geometric than this, at least. Using this volume formula, you're able to compute statistics for simple geodesics on hyperbolic surfaces. So for any sort of geodesic, or more precisely a linear combination of geodesics, you can associate a graph with any such set of simple geodesics, and you can compute sort of the number of collections of geodesics corresponding to such a graph using those volume polynomials. So in particular, that allows you to compute sorts of geodesic statistics on hyperbolic surfaces in terms of these correlators in a reasonably geometric way. And then there's the next piece is to sort of equate contributions of this type, contributions of square tile surfaces to such hyperbolic geodesic counts. And there's also sort of a geometric way of doing that. So this is all to say that you can, if you sort of pass to the geometric land, there's sort of a way of seeing these correlators arise in a more algebra geometric way. But I won't go into that here. I mean, this is just maybe to say that a more algebra geometric way of seeing these correlators exists. But I mean, this is somehow a little bit easier and more direct for the purposes at hand. Okay. So I guess the last part of this talk will be based on the Siegel-Veitch constants. So I'll just quickly try to describe how to get formulas for those. This will be much more sketchy. So the first thing I should say is that the previous framework,
Actually, Amol,
I literally just oh yeah.
Question about what you just said. I mean,
yeah.
So if you have a negatively curved metric, then of course the counts of geodesic don't be like exponential in length. But the point of Mizrahi count is that you're counting simple geodesic.
That's right.
And so you get a polynomial thing.
Yeah.
So is there some theorem? I'm not up to date on that. Is there some theorem that says that this is these counts are kind of universal, but then Mizrahi does this for constant negative curvature. Is there some theorem that says it's for variable negative curvature? There's also some result.
No, I don't. Oh, wait. You just mean the rate of growth, or do you mean the actual constant?
The actual constant in front. Yeah.
Oh, no. I think it's not. I'm not sure if it's true there. I'm not sure if the constant is the same there. If you allow the curvature to vary across the domain. I remember hearing this at some point, although I don't know the reference offhand.
I see.
Yeah.
Okay, thanks.
Yeah. Okay. Okay, so I guess, yes, this last point, we'll talk about these Siegel-Veitch constants. So the previous framework will actually do it. I mean, you can sort of rig out these Siegel-Veitch constants from the previous framework. I mean, I basically decomposed the whole surface for you and told you how to count every aspect of that. So in principle, one should be able to access these cylinder counts directly from that framework. But I'll actually outline a sort of different proof due to Askin, Maser, and Zorich around 20 years ago. That will be a little bit more geometric, maybe. I'll do it under a few simplifications. The first is that I'll only be dealing with holomorphic differentials instead of quadratic ones, although it doesn't really make, at least phenomenologically, it doesn't make much of a difference. The second is that I'll be dealing with these saddle connection Siegel-Veitch constants instead of area Siegel-Veitch constants. So remember, these area Siegel-Veitch constants counted cylinders. These saddle connections ones will count saddle connections or geodesics connecting two singularities of the surface. I'll tell you what these are more precisely in a moment. So I mean, but if this second point annoys you, then I mean, it's a theorem of Vorobet's that you can express these area constants in terms of the saddle connection ones. So I won't go into that, but I mean, it'll be enough for what we're trying to do. So okay, so let's go into it then. So we'll fix some n at least 2, and we'll fix some m, which is m1 all the way to mn. So we'll let h of m denote the associated stratum of holomorphic differentials. So these are all pairs x omega, where x is a Riemann surface and omega is a holomorphic one form on it. Well, this m here is going to just index the multiplicities of the zeros of omega. So omega is going to have n zeros with multiplicities m1, m2 all the way to mn. And a saddle connection is by definition a geodesic connecting two zeros of omega. So it's a geodesic on x connecting two zeros of omega. So we'll let this n of sc of Lx denote the number of saddle connections connecting two zeros z1 and z2 of x, such that its length is at most L. So I'm just counting the number of saddle connections connecting two zeros of length at most L. And the theorem of Eskin-Maser from 2001, which you can view as a definition of this of the Siegel-Veitch constant, is that this limit of NSC, the number of saddle connections, over it scales like L squared, and after dividing by say pi L squared, this limit will exist for almost all x. And furthermore, it only depends on M1, M2, and M. And for almost all x in some component of H of them. So it doesn't depend. If I throw out a measure zero subset of the stratum, it depends on these three numbers basically, M1, M2, and this index here. And we call this a saddle connection Siegel-Veitch constant. I mean, there are many variants of such notion, I should say, but this is one of them. Okay, so what the proof is. So how to compute these constants is the question now. So so this will proceed through a theory that was sort of
I guess we lost the speaker, right? Or
Can you hear me?
yeah, I can hear it now. Yeah.
Oh, I don't know what happened. Is the screen share working again?
Yeah, I can also see the screen now. Yeah.
Okay, everything was working. Okay. Okay, yeah. So okay, so the question then, when did I get lost?
I think on this slide, on the slide you currently have, yeah.
At about the bottom. So
Yeah.
we got most of it.
Oh, okay, yeah. So I mean, okay, yeah. So so the statement, or maybe you can also view it as a definition of these Siegel-Veitch constants, is that this so this limit of this counting function, the number, this NSC that counts the number of saddle connections connecting Z1 and Z2, it scales like L squared, and then if I divide out by this L squared, then it exists. Then it exists for almost all x in the stratum. And furthermore, this constant only depends on the order of the two zeros, the M1 and M2 that I'm connecting, and also the M tuple that's the N tuple that's the M that's indexing the stratum. So in particular, if I throw out a measure zero subset of the stratum, then it doesn't depend on x. It doesn't depend on x itself. We call this a saddle connection Siegel-Veitch constant, and there are many variants of such constants. This is just one of them. Okay, so yeah, okay, right. So how to compute these constants is the question that remains. So and the way in which that works is that is through what's often referred to as a Siegel-Veitch transform, or a formula for the Siegel-Veitch transform. So for any geodesic gamma on this flat surface X, or on this holomorphic differential X omega, we define the holonomy vector V gamma, which is, you can sort of view as the unfolding of gamma. So it's the integral of omega along gamma, which is some element of C, or I'll view it as some element of R2. And then I'll let V of X denote the set, or V of M1, M2 of X denote the set of all holonomy vectors associated with a saddle connection that's connecting zeros of X with multiplicities M1 and M2. So then for any function F that's mapping R2 to R, I'll define this F hat, which is sometimes called the Siegel-Veitch transform of F, which is which is a map from the stratum to the real numbers. And it's going to, so by definition, F hat of X is going to be the sum of F of V, where V is now ranging over this V of X, this set of holonomy vectors. So, I mean, of course, in order to make this well-defined, one needs some nice properties of F, like L1, I mean, but let me not get into that for the purposes of the sketch. So, okay, so the theorem that's important for evaluating these constants is due to Veitch, who bears the name of these constants, it's the following. So it's that there exists some constant c equals c m1 m2, so that for any f, I have this formula here. So on the left side, I have this, maybe after I normalize by the volume, I have the integral over the moduli space of this f hat against the Maser-Beach measure. And on the right side, I have the integral of f over R2 multiplied by the c. And the important point is that the c is independent of f. So, okay, the proof of this fact is based on the SL2R invariance of the left side. So the point is that the left side is some functional of f, and the claim is that this functional is SL2R invariant. This can sort of be seen by putting all of the SL2R action on the x, and then the Maser-Beach measure itself is SL2R invariant. So this functional is SL2R invariant, and then one can sort of write down all possible SL2R invariant functions with nice properties like L1 and being continuous or whatnot, and then one quickly finds that it's exactly those of this form, maybe plus a constant. Okay, so yeah, the point then is that this constant is independent of f. So now I can start varying f to start probing, to start getting things out of it. So if I let f be the indicator function that this vector v has length at most L, then on the left side, I get 1 over pi L squared. So let's divide it by both sides. So that leaves me with the statement that the C is equal to 1 over the volume of H1 of M times 1 over pi of L squared times this integral here. So this integral now amounts to the number of V's, of holonomy vectors V gamma, whose length is at most L. So I'm sort of integrating that guy over the modular space. So remember from the previous theorem, heuristically, you can imagine that this number here from the previous theorem, that this number is basically going to be almost constant over the full modular space as I let L tend to infinity. I mean, that was this theorem over here. And that's suggestive of the statement. So if I sort of believe a statement like that, then this integral will as L tends to infinity tend to pi L squared times the Siegel-Veitch constant times the volume. So that's suggestive, at least, that the C is exactly equal to the Siegel-Veitch constant I was describing before. There's a slight caution that you have to take into account here, which is that you have to be very careful about the multiplicity phenomenon, which is that you can have several gammas with the same holonomy vector. And holonomy is not taken into account in V of x, but it will be taken into account in this integral. So you actually have to be much more careful and refine this count much more precisely in order to get a statement like that. But let's believe such a statement like that, just of this form, the statement that the C is exactly the one that we're looking for the purposes of the sketch. So that means that I'm after this constant C here. So I have picked to get the C here, I picked one choice of f to be given by the indicator that the length is at most L. Let me pick another choice of f, which is really the same choice, which is that the indicator that this length here is at most epsilon, but instead of letting L tend to infinity, I'll let epsilon tend to 0 now. So I put everything into the same formula as before, and I get the C is equal to, again, 1 over the volume times 1 over pi epsilon squared times the integral over the modular space of the number of V of holonomy vectors V gamma whose length is at most epsilon. So now you can, what this is counted, so this integrand is going to be non-zero only if I have two zeros on my surface that are of orders M1 and M2 that are connected by a very short saddle connection, geodesic of length less than epsilon. So if I can imagine that if I sort of let epsilon tend to 0, then these two zeros will merge to form one of multiplicity M1 plus M2. So that will give rise to a surface in the stratum H1 of M prime, which is by definition H1 of M1 plus M2, and then I leave the rest of the remaining zeros the same, M3, M4, all the way up to Mn. So this is sort of suggestive. I mean, one could prove a statement like this, that that this integral here is given by some combinatorial factor times epsilon squared times the volume of this degenerated stratum here, this H1 of M prime. So the epsilon squared comes from the fact that, I mean, this Maser-Beach measure was Lebesgue on the period coordinates. So I have one period of length epsilon, which will give rise to an epsilon. So that will give rise to like a disk of epsilon of radius epsilon, therefore giving rise to this epsilon squared. And then I have the volume of the remaining part, which is kind of going to be like an element in this degenerated stratum. So if I plug in this sort of heuristic expression into this formula here, what I will get is that this is suggestive that this Siegel-Veitch constant is a Laurent polynomial in the Mason-Ricci volume. Actually, in particular, it's just a ratio of them, right? It's the ratio of the volume of H1 of M prime over the volume of H1 of M. So, I mean, that's sort of where that's the origin of sorts of statements along these lines. Of course, I mean, I lied to some extent. I mean, this issue of multiplicity that I mentioned before forces one to instead refine this count. I mean, one has to count in terms of configurations of homologous saddle connections, which are saddle connections that have the same holonomy vectors. And this leads to substantially more combinatorial formulas, and you will then see actual Laurent polynomials and not just, not just trivial ones like ratios. So, okay, so I guess to summarize, we had from the previous talk and this one, we had large genus asymptotics for these intersection numbers. And the proof, as I had mentioned this time, was based on sort of interpreting the coefficients of the Virasoro constraint as jump probabilities for a random walk. We had large genus asymptotics for the volumes of these moduli spaces. The proof was based on a discretization of the moduli space by the set of square tiled surfaces. You can then refine this sort of, the volume then amounts to computing the number or counting such square tiled surfaces. You can refine such counts by a stable graph. Then by decomposing the stable graph, by decomposing the surface by its horizontal foliation, you're led to a count of trivalent ribbon graphs, and this eventually expresses such counts in terms of correlators. Last time we had described statistics, how asymptotics of these correlators can be used to describe statistics for these random square tiled surfaces of large genus. And then another application is the large genus asymptotics for these Siegel-Veitch constants. Those are based on formulas for these Siegel-Veitch constants for the volumes, and those can be deduced from degenerations of the strata in the moduli space of abelian differentials. So with that, I'll stop, and thanks for your attention.
Thanks so much. Questions? Maybe I'll start. So suppose I have like a polygon with rational angles or something like that. Then the theory you explained that has to do with the counting like close to geodesics in this polygon, close saddle connection, that polygon, and so forth.
Yeah.
But if my rational angles get denominators get bigger and bigger, then this will have to do with larger and larger genus.
Yeah.
And so if I have like a triangle with irrational angles, is the asymptotic formulas, they say something about
yeah, I don't know how the asymptotic translates there. So I mean, it's also I would like the answer to be yes, although I'm not sure if it is, to be honest. I've not seen any such results along those lines. I mean, because I'm not sure to what extent you can approximate the dynamics of some polygon with irrational angles by one with rational angles. I mean, it's partially due to the way in which the limits are being taken here. Yeah, I don't know.
Fair enough.
Sorry.
Thanks. No, fair enough. Fair answer. More questions?
Sorry. What about let's say if you have a semi-simple Koch-F-T, then so in principle the correlators could be written in terms of correlators of just a point. So could you have some asymptotic, or like also there are Virasoro constraints? Could you write asymptotics for correlators for some more general targets?
Oh, I haven't tried it. I mean, yeah, I mean, I was asked this question by several people actually. Can you use this? I mean, the method, as you can see, is fairly robust. If you alter the Virasoro constraints to consider some other algebraic geometric invariants, can you start to prove asymptotics with them? I haven't tried, although, I mean, as I said, the framework is fairly robust, so it's plausible.
I see, I see.
All right. If we don't have any more questions, then let's all thank Amol very much for very exciting couple of talks. And I don't know how exactly we can clap online, but you can imagine we do. And well, there's you can say exactly pictograms and stuff. Well, that's will be all for today, and we'll meet again next week. Thanks everybody.
Thank you.
Thanks Amol. That was great. Thanks.
You.
Thank you.